Good. This is the last sort of video in this state machine lecture. And what I want to do here is a few different things. So first I want to do one more design example, and then I kind of briefly going to cover a few other interesting or useful concepts, namely the difference between blocking and non-blocking assignments, and also how to deal with state machines that are complicated. Okay, good. So here, this string recognizer example is actually quite similar to something you're going to do in the lab. So what you're asked to do is to recognize the string 101, and this input, essentially imagine that it's coming in bit by bit, starting here with this first bit 1 on the left hand side. So obviously, again, before watching me do this, try to solve this problem yourself. I think it's going to be very helpful. Good. So here, well, what's the output? So you're recognizing 101. So if all you've seen is a 1, your output is going to be 0. Well, if you've seen 1, 0, your output's still 0, 0. Now, okay, there's a 1 because it's a bit more interesting. So you've seen 1, 0, and this is of course 2. So now you've seen the series 1, 0, 1. Then it continues with a 0 and a 1. So again, this is true because once again you've seen 1, 0, 1, and so the output is true. And you can check for yourself that in the following the output will be false. So don't see any other occurrences of 1, 0, 1. But that's the basic idea, right? Whenever you've seen 1, 0, 1, you output true, else you don't. And of course, as you've seen here, you can sort of reuse this 1, both as the last one in the first 1, 0, 1 and as the first one in the following 1, 0, 1 string. Okay, so what's the state machine here? The way I have it is basically there's 3 states. One that I'm going to call none, sort of the initial state. I'm going to encode this as 0, 0. Then there's another state that I'm going to call 1. I'm encoding it as 0, 1. And what is that state? It basically means as long as I haven't seen any 1s, I'm in this none state, right? As soon as I see a 1, I go to this 1 state because 1, 0, 1 starts with a 1. So that's the first interesting event. And so starting here, I can say if I see just zeros, well, I'm staying in this state and I'm outputting 0, and I can also apply a reset here, of course, as always. On the other hand, if I'm in the state, the none state, and I see a 1 input, I can go over here, and I'm still outputting 0 because I haven't seen the string I'm looking for. Now, if I see another 1, I'll stay here. It's kind of like I'm starting over. I still have 1, 1, and so I'm just here. But if I'm then seeing a 0, I'm seeing a 0, I'm outputting 0, and I'm going to this other state, you could call 1, 0, where I'm outputting, and I'm also actually going to encode it as a 1, 0, but 1, 0 is basically just because I've seen a 1 followed by a 0. If I see a 1, I can go back here. So that's what I was looking for, right? 1, 0, then followed by a 1. So I'm going back to the 1 state, but I'm outputting a 1. So that's the case. I'm going back here because, of course, that 1 that I've just seen could, again, be the beginning of a new string, 1, 0, 1. On the other hand, if I was here, 1, 0, and I see a 0, then I sort of have to start over, and I'm going here. Okay? So that's the machine that I have. And I think, again, the difficult part is just to kind of figure out what this description at the top, what you're asked to do, and sort of identify the relevant states, understand that you don't actually need the 1, 0, 1 state, right? I think that would be a common mistake, would be to add a fourth state, or it's not necessarily a mistake, a common complication. I mean, it's a mistake in the sense that your state machine, if you add that state, will be bigger than the one I have here, and that you always want to make it as small as possible. It's not a mistake in the sense that it might still produce the correct logic. But the key thing here is, but as I said, I mean, what's nice here is that you don't actually need that 1, 0, 1 state, because once you're in the 1, 0 state and you're seeing a 1, you can just set output to true and then start over in this 1 state. Okay. So just for completeness, I also want to sort of derive, or ask you to derive, the state table again from the state diagram. I mean, this should now be pretty straightforward, so there's no real thinking involved here, just copying information from the diagram to the table. The state table looks like this. So you have present state 1, present state 0, the input, then you have output, next state 1, next state 0. I'm just going to fill this in. Okay, so that's my state table, and from the diagram you should be able to read off that you get the following values on the right hand side. And of course we only have 3 states, so there's a bunch of x's down here. And then from this state table, you can either use k-maps, or maybe you just can look. Maybe you can just look at the state table and find that output is equal to present state and in. Next state 1 is equal to present state. Sorry, this was present state 1. This was present state 0, and not in. And then next state 0 is just in. Okay? So hopefully you were able to solve this problem yourself, because this is very similar to something you'll do in the lab. Okay, another point that I want to make is that sort of emphasize or kind of explain a little bit this distinction between a blocking statement and a non-blocking statement. So the blocking statement, which is just the equal sign, assigns a value immediately, while the non-blocking sign, which is this sort of leftwards pointing arrow, first looks at all the right-hand sides and then does all assignments in a list of assignments simultaneously, right? And you can see the difference here, or why this matters, in these code examples down here. Okay, so on the left-hand side, I'm trying to do a swap operation where I have 2 values, value 0 and value 1, and I want to exchange the values between them, such that value 0 at the end becomes value 1 and value 1 becomes value 0. And I have 2 different ways of doing this. I want to do this at, in a clock system, sort of at the edge, the positive edge of a clock. So in this left-hand code, which is going to be the code that essentially doesn't work, I'm using the blocking statement. So what's going to happen here is that in this, I'm going to execute this code in the if block here, line by line. So in the first step, I'm going to take value 1 and write it into value 0. And then, of course, this second statement here is completely useless, because values 1 and 0 have become equal in the first place. So all I know at this point is what the original value of 1 was. On the other hand, and this is very important, on the right-hand side here, this is sort of the correct way of doing it. So this is good, because here I'm using these non-blocking statements. And what happens here is that these 2 swap operations are literally executed at the same time, such that really this executes a swap where value 0 where value 1 is written into value 0 and the old value 0 is written into value 1. And so at the end here, out is actually the original value 0, while here it's just the original value 1. So this code on the right hand side works, does the swapping of the values correctly, while the code on the left hand side does not do it correctly. So in practice, there's some simple rules as to how to use these two different symbols. So in a combinational logic block, so basically in always at star, you can always use this equal sign, so the blocking statement. But in sequential logic, in always at pos clock, always use the non-blocking version. Okay, so never mix them in one block. And if you follow these rules, essentially use equal in always at star in combinational logic, and this arrow here, the non-blocking statement in sequential logic, you'll be fine. But I think it's very important, if you don't, it's a common error not to use the non-blocking statement, so just use the equal sign in the always block, and as we've seen in this previous example, that will very likely sort of mess up the operation of your code. Good, so I want to make one more point here, which is kind of thinking about how to design state machines that are potentially large or complicated, right? And the basic idea is going to be that you're going to break this state machine down into smaller pieces that are more tractable, right? So here's an example. So you have a psychic tester. So somehow there's a machine that generates patterns of 4 values on or off, so it's 4-bit numbers. And there's a user who guesses patterns. And if you guess 8 of these patterns in a row correctly, then you're a psychic. And so the machine that you're trying to build is sort of a tester for whether you're a psychic or not. And in some ways, the straightforward way of doing this would be to think of something like this. You say, well, there's how many? There's 2 to the 4 equals 16 different potential patterns that the machine can generate. So that's the and you have to make 8 guesses. So 0 to 7. So maybe you could do a state machine with 16 by 8 states, where each state essentially corresponds to a combination of one pattern. So this would be pattern 0, guess 0, then the next one would be pattern 0, guess 1, and down here in this direction you'd have pattern 1, guess 1, etc. So 128 different states. And it might work just fine, but it clearly is a very, very inconvenient system to build. And so what you should try to do instead is to kind of think about what the pieces are that constitute the full machine, and try to build and test those individually, right? And again, it'd probably be good to think about what these pieces could be before listening to me. But one way to kind of think of this would be to say, okay, so you have, first of all, you have user input, and that's the guess. And so essentially you have like 4 switches plus a go button or something like that. And that generates the guess. You also are generating the actual pattern. So pick a pattern. And that's a FSM. Oops, correct. An FSM with 16 states, right? As we said, 2 to the 4 different combination, 16 states. Then there's probably some combinational circuit here that compares these two. So we want to check the guess. And that's just combinational. Then we say, okay, if the guess is right, we have another state machine over here that counts the correct guesses. And so that's just 8 states. So it basically says if this is right, you increment, else not. And then you go to the next pattern. Okay? That's essentially one way in which you can break down this sort of complicated system into smaller bits, and now instead of designing one state machine with 128 states, you're essentially just designing 2 small machines with 16 and 8 states respectively. And I think this kind of approach of breaking down complex systems into smaller bits and pieces and also testing each of them individually is going to be really important for the more advanced labs.